Hello students, so here we are with lecture 8 of Haloalkanes and Haloarenes class 12. So SN1 reaction mechanism. Here S stands for substitution, N stands for nucleophilic and 1 stands for unimolecular. So basically it is a unimolecular nucleophilic substitution reaction. So what is the example of this reaction? Which reaction follows this mechanism? So when tertiary butyl bromide is reacted with nucleophile OH, which is provided by aqueous KOH or aqueous NaOH, gives you tertiary butyl alcohol plus bromide ion. So basically the reaction between tertiary butyl bromide and hydroxide ion to give tertiary butyl alcohol follows SN1 reaction mechanism. Now what is the kinetic expression? So this is a two-step reaction and it follows a first order kinetics. So that means rate is proportional to the tertiary concentration of tertiary butyl bromide. The rate of the reaction depends on the concentration of only one species, that is tertiary butyl bromide. Hence it is called substitution nucleophilic unimolecular reaction. Clear? So this mechanism follows two steps. In step 1, the formation of carbocation takes place. The carbocation is formed, and in the step 2, the tertiary butyl alcohol is formed. So step 1 is a slow step that leads to the formation of carbocation plus carbon-bromine bond breaks and the bromide is liberated. Bromide is a leaving group. Then on the carbocation, OH nucleophile attacks in the second step. It may attack from the front side or it may attack from the back side, and tertiary butyl alcohol is formed. So basically it follows a two-step mechanism. The first step is a slow step. The carbon halogen bond breaks, undergoes hydrolysis, and second step is a fast step. The nucleophile attacks and the tertiary butyl alcohol is formed. So basically if you see the mechanism in detail here, in the formation of carbocation is a rate determining step and planar tertiary butyl carbocation is formed. Okay. So here you see the carbon-bromine bond breaks. Carbon and bromine bond is a polar bond because bromine has got more electronegativity than carbon, gets a delta negative charge. This carbon gets a delta positive charge, and when the nucleophile approaches, then this carbon-bromine bond breaks and carbocation is formed. And bromide is the leaving group. So because the nucleophile here is a weak nucleophile, it takes time to approach the carbon, and therefore first the carbocation is formed, and then after that in the second step the OH nucleophile approaches the carbocation. This carbocation is having sp2 hybridization and the carbon carries the plus charge. So in the second step, what happens? This carbocation, the OH nucleophile attacks on the carbocation. Now here front side and back side both are available for forming the bond. So OH can attach from the back side, it can attack from the front side. When it attacks from the back side, it leads to the inversion configuration. And when the product is having the inverted configuration, that means, and when it attacks from the same side where the nucleophile was earlier attached, then it is called retention configuration. So the products formed are having 50% inversion configuration and 50% retention configuration. So as carbocation is planar, the attack of nucleophile can happen from both the sides, front side and back side. And the product form is 50% inversion and 50% retention. Clear? Now, if the substrate is optically active, if the substrate is optically active means which contains chiral carbon. Chiral carbon means the carbon to which 4 different groups are attached. Okay. So then the product form will have 50% inversion and 50% retention, and the product form will be having the mixture of 50% inverted product and 50% retention product. That means 50% of the levorotatory product and 50% of the dextrorotatory product. And the mixture of the 50% levorotatory and 50% dextrorotatory is called racemic mixture. And racemic mixture is what? Optically inactive. So if the reactant or the substrate here is optically active, then the product form will be optically inactive because it will be a racemic mixture. Clear? So if substrate is optically active, then product is optically inactive. Why the product is optically inactive? Because the product form is having 50% retention configuration, 50% inversion configuration. That means 50% product is dextrorotatory and 50% is levorotatory. So because of the external compensation, the rotations get cancelled and hence it is called racemic mixture. Clear? Now, what are the important points for SN1 reaction? Let us see. So, firstly, we said the reaction happens in what? Two steps. And it happens with a weak nucleophile. The reaction requires weak nucleophile. So, weak nucleophile, because the nucleophile is weak, what happens? First, the carbon-bromine bond breaks, the carbocation is formed. That means till the OH nucleophile reaches the reactant to substrate to form bond, the reaction starts. The substrate starts the reaction. And this carbon-bromine bond breaks, the carbocation is formed. Then in the second step, what happens? The carbocation gets attacked by this OH nucleophile. It can attack from the back side, it can attack from the front side, and it forms a product with 50% inversion and 50% retention. So basically, which nucleophile is used here? Weak nucleophile is used. Okay. It cannot happen with the strong nucleophile. Okay. Like alkoxide ion, like water, such nucleophiles are used. Then step 1 being a slow step determines the rate of the reaction. So how do you write the rate expression? Rate expression is equal to K into Rx. That means K into the concentration of tertiary butyl bromide to the power of 1. So what will be the molecularity of the reaction? The molecularity of the reaction will be the only one molecule is participating, one molecule of tertiary butyl bromide is participating in the reaction. Therefore, the reaction will have molecularity 1. And what will be the order of the reaction? Order will be decided on the basis of the rate expression. The rate is equal to K into Rx to the power of 1. So, power to which the concentration term is raised in the rate expression gives you the order of the reaction. So, here order of the reaction is going to be 1. So, order of the reaction is 1. Molecularity is also 1. Clear? Then rate of the reaction is directly proportional to the stability of the carbocation. The rate determining step is the first step which leads to the formation of carbocation. Okay. Then more stable the carbocation, more will be the rate of the reaction. Okay. So if you compare between 3 degree, 2 degree, 1 degree, tertiary, secondary and primary, who will have more rate of the reaction? The tertiary will have the maximum rate of the reaction. Which reaction? SN1 reaction. Clear? So, solvent used here will be what? Polar protic solvent. So, that means the solvent which is polar and that contains proton. Okay. Then if substrate is optically active, then product would be what? Optically inactive, because the product will be made up of the 50% of the retention and 50% of inversion. That means it will be made up of the two enantiomers. One is dextrorotatory and one is levorotatory. So because of external compensation, the rotations will cancel out and hence it will be optically inactive and it will be called racemic mixture. Okay. Now let's see the salient features of SN1 mechanism. It is a two-step mechanism. As we said, then hydrolysis of the CX bond is slow and reversible. So first step will be what? To form the carbocation intermediate. What is the first step? To form the carbocation intermediate. So carbon halogen bond will break and carbocation will be formed. Then second step is what? Attack of the nucleophile on the carbocation intermediate in the fast second step to form the product. So attack can happen from the back side, attack can happen from the front side. Then SN1 reaction proceeds mainly with the racemization if carried out in the chiral carbon or the optically active substrate. So this we have said 2-3 times that if it is a optically active substrate, the product form will be optically inactive because it will contain 50% of intention, 50% of inversion configurations. It will be made up of two enantiomers that are rotating the light in the opposite direction Hence, the iterations will cancel out and it will be optically inactive, right? It will be made of the racemic mixture. Clear? So, the salient features are clear. It is a two-step mechanism. Then, first step is the slow step, the rate determining step, and it leads to the formation of carbocation. Second step is the attack of nucleophile, which can happen from front and back side, both available. And if the reactant is or the substrate is optically active, the product form will be optical. So this is energy profile diagram for SN1 reaction. The diagram between potential energy and the reaction coordinates. So this first point you see reactants. Here this is the energy of the reactants. The reactant here is what? Tertiary butyl bromide, let's say. Then first what happens? The carbon bromine bond breaks. The transition state is formed where carbon bromine bond is about to break. So reactants get the energy, they reach here, they reach the first transition state where carbon bromine bond is about to break. And then what happens? The carbocation is formed. This is a slow step and the formation leads to the formation of carbocation. Then what happens? The OH nucleophile attacks on this carbocation and carbon OH bond is about to form. So when the carbon OH bond is about to form, the transition state is reached and then the carbon OH bond is formed and the product is formed. Okay. So therefore, here you see the energy of the reactant was here and the energy of product is here. So the energy of product is less than energy of the reactant and the difference in energy of the product and energy of the reactant is called delta H. That is the heat of the reaction. So this shows it is an exothermic reaction. And another thing you see here is delta E1 and delta E2. So delta E1 is what? Activation energy 1 and delta E2 is activation energy 2. So activation energy means the difference in energy of the transition state and the energy of the reactants. Difference in energy of the transition state and energy of the reactants is called activation energy. So activation energy 1 is greater than activation energy 2. So here the reactant is about to break the bond of carbon bromine and the activation energy required is more. Here it is a transition state, here it is a carbocation. So energy required to form the transition state is less because it is already in the reactivity mode. Clear? Okay. So factors influencing SN1 and SN2 mechanism. For SN2 mechanism, first factor is what? Nature of substrate. So for SN2 mechanism, it is favored in primary alkyl halide, while SN1 mechanism is favored in tertiary alkyl halide. So why is it so? The SN2 mechanism, the bond breaking and bond forming is happening simultaneously. So the nucleophile has to approach and still the carbon halogen bond is not broken. So when the nucleophile has to approach, it cannot approach from the same side. Because when he approaches from the same side, from the front side, then what will happen? There will be repulsion. And if it is approaching from the back side, there is alkyl groups present. So that means they cause what? They cause hindrance, steric hindrance. So when it is methyl uh, group, then there is no problem. Ethyl group, the number of carbon atoms increase. Then isopropyl, still the number of carbon atoms are more. Tertiary butyl, the crowding will be still more. Therefore, the crowding will call destabilization. Okay, so the crowding will create a problem in formation of transition state and therefore it is favored with primary alkyl halide. While SN1 mechanism involves what? Formation of carbocation. This is happening in two steps, so no issues. Steric hindrance will be not a problem. But then when which will have more favoring effect, the in methyl group what will be formed? The first step, methyl carbocation will be formed. If you are taking ethyl halide, then ethyl carbocation will be formed, isopropyl carbocation will be formed, and tertiary butyl carbocation will be formed if tertiary butyl bromide is taken as the substrate. Okay. So here you see the carbocation stability is going to affect the rate of the reaction or their formation. So more the stability, more will be the possibility of their formation. So the SN1 mechanism will be favored with the tertiary alkyl halide. Clear? So second factor on which the rate of the reaction depends is the nucleophilicity of the reagent. So more powerful nucleophile attacks the substrate faster and favors the SN2 mechanism. So if it is a strong nucleophile, it will quickly react with the substrate and the reaction will progress. So it follows SN2 mechanism. But if it is a weak nucleophile, what happens? It takes time to react. Okay. Therefore, first the substrate is forming a carbocation and then the nucleophile approaches and it forms the product. So basically SN1 mechanism happens when it is a weak nucleophile, and if it is a strong nucleophile, SN2 reaction mechanism happens. So that is how the nucleophilicity of the reagent affects the factor that affects to decide whether SN2 mechanism is going to happen or S1 mechanism. Then solvent polarity. So aprotic solvents or solvents with a low polarity, they will do SN2 mechanism. Why? Protic solvent deactivates the nucleophile by stabilizing it. Okay. So aprotic solvents, which are the aprotic solvents like DMF, dimethyl formamide, or acetone, the aprotic solvent where the hydrogen proton is not released. Okay. So they will prefer SN2 mechanism. But if you are taking polar protic solvent, they are going to prefer SN1 mechanism, because polar protic, if the solvent is protic, then it can form hydrogen bond or get solvated. So they may affect the formation of the product. Okay. So solvent may react with the carbocation or it may cause hindrance in the formation of the product. So that favors SN1 reaction. Okay. Here. Now let's see the difference between SN1 mechanism and SN2 mechanism. Order of reaction. SN1 mechanism, first order. SN2 mechanism, second order. Then step of reaction. SN1 mechanism was having how many steps? 2 steps. While SN2 was having 1 step. Then kinetic expression. S1 mechanism is what? Unimolecular. SN2 mechanism is bimolecular. We understood this, I have already explained. Then nature of substrate, SN1 mechanism, which substrate, what will be the order of reactivity? 3 degree, then 2 degree, then 1 degree. So 3 degree will tertiary will favor which one? SN1 mechanism. But order of reactivity for SN2 is what? 1 degree, 2 degree and 3 degree. That means 1 degree will favor which one mechanism? SN2 mechanism. Then nucleophilicity of the reagent. SN1 mechanism happens in the presence of weak nucleophile, while SN2 mechanism happens in the presence of strong nucleophile. Then solvent polarity. Polar solvents will favor which mechanism? SN1 mechanism, but aprotic solvent will favor which one? SN2 mechanism. Right? Clear? So as we said, steric hindrance, SN1 mechanism, the rate of the reaction is independent of steric hindrance. Nothing to do with the steric hindrance, because in the first step the carbocation is formed, and the steric hindrance problem is when the bonds are being formed and the nucleophile is approaching. So here already the carbocation is formed, so there is no such hindrance here. But for SN2 mechanism, the rate of the reaction is inversely proportional to the steric hindrance. So more the steric hindrance, lesser will be the rate of reaction. Therefore, this SN2 mechanism will be favored in alkyl halide, primary alkyl halide. Then stability of the carbocation. SN1 mechanism, the rate of the reaction is directly proportional to the stability of the carbocation. More stable the carbocation, more will be the rate of the reaction. Then rate of the reaction is independent of stability of the carbocation for SN2 mechanism. Then if it is an optically active substrate, then the product formed in SN1 mechanism will be what? It will be a racemic mixture containing 50% of retention product and 50% of inversion product. While for SN2 mechanism, the product formed is optically active but 100% inversion. While here the product formed is a racemic mixture, therefore it is optically inactive but having 50% retention and 50% inversion. Okay. Now let's see the energy profile diagrams. Here for SN1 mechanism, the energy profile diagram is having 2 peaks, while here it is just 1 peak. So this shows 2 steps and this shows 1 step. Okay. And then it is having 2 activation energies here, delta E1 and delta E2. while here it is having only one single activation energy. Okay, here we are having two transition states, but here the transition state in SN2 mechanism is only one transition state. Okay, both the reactions are what? Exothermic, but then these are the differences. Right? Clear? Okay, thank you.